Okay, so new stuff for today. I'm going to be going through a couple word problems on integration and accumulation. So we'll be using relationships with derivatives and integrals to interpret the meaning of some rates of change and derived rates, and estimating derivatives and integrals graphically. So instead of just working this out, I'm going to start calling on people to do individual parts of this. So let's see what I've got. I've got Abby, Nikita, Nini, and Kyle on Skype. And Andrew, Eric on Zoom. Okay, so first thing we're going to do is we're going to take a look at what was given. So this is calories per minute, which is F of T. And our x-axis is T measured in minutes. So we could say for 0 to 4, F of T is given using this equation. But after 4, we're told that it is a piecewise linear function, which means there's different pieces of this equation that are linear. So I have 1, 2, 3, 4 different equations. So 1 from 4 to 12, 1 from 12 to 16, 1 from 16 to 20, and 1 from 20 to 24 that are all different linear functions. Each one would be measured in calories per minute. So a rate of how many calories you're burning each minute. Okay, any questions on what we were given? All right, then I'm going to start at the top of the order over on Zoom, and we'll make our way to Skype. So starting with Andrew, I want to get an estimate for the derivative at 22 of this function. Oh, I need to turn you up again. Okay, so I heard it, but I'm not sure the recording did, but you're right. So we need to get the slope of this line. So how can we get the slope of this line?
20, 24 minus, oh no, 3 minus 15 over 24 minus 20.
Okay, awesome. So that's 3 minus 15 over 24 minus 20. Is negative 12 over 4 or negative 3? Okay, so a derivative is a slope at a point. For a linear function, so that's for a line, the slope at all of the points on the line will be the same. So that means we can just get the slope of this line from 20 to 24, and that will be the slope for all points between 20 and 24, including 22. Any questions on part A? That was perfect. Okay, I'm going to jump over to Abby. Abby, what are my units for part A? So we found the slope of f. What should the units be?
Calories per minute.
So f is already in calories per minute. So if I derive it, what will happen?
Minute.
Not just minutes. So we took a derivative, so that's our change in y over change in x. So what are our units for y, and then what are our units for x? What are the units used for the y-axis right now?
Calories per minute.
Calories per minute. So this is calories.
Oh, calories.
Okay, this is calories per minute over, what's our units for x?
Minute.
Minutes. This is calories per minute per minute. So if I simplify that, this would be calories per minute times 1 over minute if I'm dividing by minutes, or calories per minute squared.
Okay.
Okay. And every time that I'm deriving, I'll divide the units of y by the units of x. Anytime that you are integrating, you'll end up multiplying the units of y times the units of x. So if we integrate f right now, then my units would be minutes. If I derive f right now, our units will be calories per minute squared. And if we just plug in a value, then we'll be calories per minute. Any questions on part A, units? Okay. For part B, we want to know at what time is f growing, increasing at the fastest rate, and then show the reasoning that supports our answer. So first, I'm going to jump over to Nikita. Nikita, can you give me 2 time intervals, so from what time to what time, where f is increasing? So where on this graph is f increasing? Nikita, are you there? Okay, I think we've lost Nikita, so I'm going to jump to the next person in the order. Nini? Nini, where on this graph is our function increasing?
9 to 15.
Okay, so from x equals 12 to x equals 16.
Yes.
Okay.
And yes.
And then one more.
From the beginning to x equals 4.
Okay. And from t equals 12 to t equals 16. Okay, so what we're going to do is we're going to take a look at how fast this is increasing. So that's my derivative of f from 12 to 16. And we'll see if we can compare that to the derivative from 0 to 4. Okay, so I'm going to jump over to Kyle. Kyle, what's my slope of this graph between 12 and 16?
And 16, okay, so 15 minus 9, wait,
Okay, I heard it. 15 minus 9 over
over 16 minus 12.
16 minus 12. Okay, so what is that?
That's the slope, so it's 15 minus 9, 16 minus 12. It's 3 over 2.
Okay, 3 over 2 is my slope on 12
Calories per minute squared.
calories per minute squared, you're right. Okay, and then I'm going to jump over to... Okay, I'm going to jump over to Eric next. On the interval from 0 to 4, what's f prime?
Nine minus 1 over 4 minus 0.
Close. So f prime is not linear, so we can't just do an average slope. Hint with my laser pointer here, but we've got a function that's true for 0 to 4.
Oh, put the t value in.
Okay, so what would the derivative be?
Negative 3 over 4 t squared plus 3t.
Perfect. Okay, so this is a general form. If I want to know when this is maximized, so when is this as big as possible, then I would have to optimize this result. To optimize anything, I derive it, set the derivative equal to 0, and solve for x. So that's what I'm going to do here. We're going to derive this one more time. So this is on our interval from 0 to 4. So we could say f prime prime on 0 to 4 is equal to the second derivative of this. So if I derive one more time, what's going to happen?
Negative 3 over 2 t plus 3.
Okay, then I'm going to set this equal to 0, and we'll solve for t. So if I do, 0 equals to negative 3t over 2 plus 3. Therefore, negative 3 equals negative 3t over 2, or negative 6 divided by negative 3 is 2. T equals 2. Okay, I do need the test and see for my second derivative at 2. Am I changing from positive to negative or negative to positive? That will tell me whether f prime is a maximum or a minimum. So we've already proven that the slope is 0. But if the slope is 0, that could be a maximum or a minimum.
Mr. Brown,
Yes,
Mr. Brown,
Nikita?
and like connection issues, so I couldn't hear who you said. Can you please explain? Like starting from part B.
Let me finish off where we are right now, and then I'll come back.
Okay, so
Okay, so I'm going to do a second derivative test. We're going to plug this t in to see whether our function's changing from positive to negative. So we can plug in any value that's less than 2. So I'm going to plug in 0, and I get a positive value. And any function that is greater than 2, if I plug in 3 right now, I'll end up with a negative value. So that means our function changed from increasing to decreasing, which makes this a maximum. So maximum at t equals 2. So that maximum would be what happens if I plug 2 into our equation. So I could say f prime at 2 is equal to 2 squared is 4. My 4's will cancel, so that leaves me with negative 3 times 2 squared over 2, over 4. Plus 3 times 2. So that's negative 3 plus 6 is 3. Okay, so we've got 2 points where we were increasing. My largest increase on 0 to 4, we found was at t equals 2, where we were increasing at a rate of 3 calories per minute, or calories per minute squared. We were also increasing from 12 to 16 at a constant rate of 3 over 2 calories per minute squared. So when are we increasing, what time are we increasing as much as possible? We're back at the top of the order. So Andrew.
Yes.
What time is our function increasing as much as possible? We said from 12 to 16 is a constant here, and then we found the largest time from 0 to 4 was here at t equals 2. So given all of that, when is this function increasing at the greatest rate?
0 to 4.
0 to 4, you're right, but more specifically, what time? So what time on 0 to 4 is this increasing as much as possible?
Oh, when t equals 3, t equals 2.
When t equals 2, where we'll be increasing when t equals 2 at a rate of 3 calories per minute squared. Okay, perfect. So I'm going to double back and explain that for Niall and Nikita who are just joining us. So what we're looking for here is when f is increasing at the greatest rate. So the first step is to try and figure out when f is increasing. We're increasing from 0 to 4 because our function is going up, and from 12 to 16 because our function is going up. From 12 to 16 is a line, so that means our rate of change, our slope, will be constant. So to find it, we can just get the slope of the line, which is y2 minus y1 over x2 minus x1, which gave us 3 over 2. So from 12 to 16, our rate was a constant, 3 over 2 calories per minute squared. Okay, but we're also increasing from 0 to 4, and that rate is not constant. You can see it's curved, so that means our slope is changing. We were given a function for that part of the curve. F of t equals this equation, which if I derive it, will give us a general form for the slope on 0 to 4. So on the interval from t equals 0 to t equals 4, our slope is negative 3/4 t squared plus 3t. If I want to figure out when the slope is maximized, we can optimize that slope. So to optimize any function, we can derive it, set the derivative equal to 0, and solve for x. That'll give us any critical points, points where the slope is 0. And we can then test to see when the slope is 0, did we change from positive to negative or from negative to positive, which would tell us whether this is a maximum or a minimum. So I derive this one more time. If I derive f prime, I'll get f prime prime, which is negative 3 over 2t plus 3. If we set that equal to 0 and solve for t, we got 2. So at t equals 2, f prime has a critical point. And if we do a second derivative test, I'm plugging in values into our second derivative right now. So if I plug in 0, I get a positive value. If I plug in 3, I get a negative value. So that means our f prime prime changed from positive to negative, which means f prime changed from increasing to decreasing at 2, which means this must be a maximum. We changed from increasing to decreasing at 2 for f prime. So if f prime is maximized at t equals 2, that's when our calories per minute squared are growing the fastest on the interval from 0 to 4. At t equals 2, if we plug it in to our equation for the derivative, f prime at 2 would be 2 squared is 4, so my 4 and 4 will cancel, so that leaves me with negative 3 for the first term, plus 3 times 2 is 6. So that's 6 plus negative 3 is positive 3. At t equals 2, we have 3 calories per minute squared that are being burned. So our calories per minute that we're burning is increasing at the fastest rate at the time t equals 2, at exactly 2 minutes into this person's workout. Any questions on what we did? Okay, that was the hardest part of this, I think. So I'm going to look at the scoring guide for A and B, then we'll keep going. So this is what College Board gives the teachers that are supposed to score you on your AP exams later. So here we've got sample work on the left side, and then on the right side is your point distributions. This is how you would be graded. Okay, so for this one, you've got 1 point for your setup, not your answer, of f prime 22. So if you said f prime 22 is equal to y2 minus y1 over x2 minus x1, and you gave the right units, calories per minute squared, then you would get full credit for that point. Okay, for part B, we had to get a derivative for 0 to 4, so that was get this derivative for 1 point. Prove that we have a maximum of t equals 2 on 0 to 4. So we did that with the second derivative test, which they also did here in the work, so that's another point. Show that that slope is bigger than what happened for 12 to 16. So we did that by getting the slope here from 12 to 16 of our line. And then give our answer. We're increasing at the greatest rate at t equals 2. Okay, my point in showing to you this, we're really a year ahead of time, is for next year on your AP exams, regardless of whether you choose to take Calculus AB or if some of you are choosing to take Calculus BC and test out with me or statistics, you're graded on your process, not your answer. So your answer for this is only 1 point out of 4. Okay. For part C, I want to know the total number of calories that we burned from 6 to 18 minutes. Okay, we are to the top of the Skype order now, so we're back to Abby.
Yes.
Okay, right now we have a function f of t, which is calories per minute. If I want to get from a function of calories per minute to a function of calories, do I need to derive or do I need to integrate?
Integrate.
Integrate. Every time we integrate, we're going to multiply our axis of y times our axis of x. If I integrate f of t from 6 to 18, our units will go from calories per minute, which is f of t, and then when I multiply times dt, that'll be minutes, which will cancel, and I'll be left with calories. So if I want to know how many calories we burned from the 6 minute mark to the 18-minute mark, I would have to integrate our function here from 6 to 18. Okay, now I don't have a function given. What I've got is a graph. But because integration is area underneath the curve, we can split this up into shapes and just get the area that way using algebra. So I'm going to stick with Abby for the first part. From t equals 6 to t equals 12, what shape could I use to get the area underneath the curve?
Rectangle.
Rectangle, perfect. So here's our rectangle. What are the sides of our rectangle?
The length is 9.
Okay. And the width is?
And the width is 6.
6, perfect. Okay, I'm going to jump over to the next person in the order. So that is Nikita. Nikita, from 12 to 16, what shape could we use?
We could use like what's the name of that semi-triangular shape? I forgot the name.
Trapezoid.
Yeah, trapezoid.
Okay, we can use a trapezoid.
Trapezoid.
So I'm going to add, let me do this in a lighter shade of red maybe, because that's a little hard to see. Do this in orange, I guess. So if I want to get the area of this trapezoid, what do I have to do?
I think you take the slope.
So for the area of a trapezoid, we need the average of the heights and then multiply by the base.
Yeah, so it's 16 minus 12. Oh wait, 16 plus 12 divided by 2
Okay.
times 4.
Times 4, perfect. And then the last one, from 16 to 18, what shape can I use, Nidhi?
16 to what?
What shape can we use to get the area from t equals 16 to t equals 18?
Rectangle.
Rectangle. What are my side lengths?
Y is 15 and X is 2.
Okay. So I'm going to stick with Nitty and we'll finish this one off. Um, our first area in green is how much?
First area in green.
Yep.
54.
54. Okay. Um, our second area in red is how much?
56.
Okay, so I've got 18, 28, 14 by 4. Okay, 56. And our last one in blue is how much?
30.
30. Okay, if I add all of that up, what am I left with?
140.
Um,
No.
okay, I've got
Hello?
54.
Can you hear?
I can hear. Can you say it one more time?
140.
Okay, that was 140. I'm going to double check really quick. So we had 2, 28. That's fine. Okay, we don't match what I had originally. I'm trying to figure out what we did. Oh, okay. We've got a problem with our trapezoid, actually. So let me go back. These should be y values, not x values. Okay, so this should be 15 and 9 then. Okay, so that gives us, I've got 24 over 2 is 12 times 4 is 48. And if I add that up, that'll give us 132 instead. Okay, sorry about that, didn't catch that early enough. Any questions on our areas here?
No.
Okay. So again, my units for this would be calories. Since when we integrate, we multiply our units together. Calories per minute times minutes is calories. Okay, here's their scoring guide. So, one for your methods, that's splitting this up into different areas. They actually use the same method we did, which is nice. So that's rectangle, trapezoid, rectangle. Okay, and last part, part D. We are changing the settings that the person is now burning f of t plus c calories per minute. So we're going to add another calorie per minute on our machine. If this is a stationary bike and you're trying to use it to work out, we're increasing the resistance so that we will burn an extra c calories per minute, every minute. For this setting, I want to find the value of c so that the average calories per minute burned is 15 calories per minute. Okay, so I'm going to start off with, let's see, we're at Kyle. Kyle, do you remember what our average value formula is? So this was 2 or 3 weeks ago. It's been a while.
Average formula?
Yep, the formula for the average value of a function.
No.
Okay, so When we get the average of a set of numbers, what we usually do is we sum all of the numbers in the data set.
Oh, like find the mean.
Yep, and then divide by the number of numbers. When we've got a function, we do almost the same thing. So what I'm going to do is I'm going to integrate my function from a start point to an end point, from A to B. But then after I integrate, I'm going to divide by the total amount of x values that we've covered. So that's divide by b minus a. So what that does, if you want to think of this in terms of physics, if f of x is a velocity, when I integrate, I would get displacement, right? But if I divide by the total amount of time that we've covered, that would be my distance over time, brings me back to velocity. My units do not change for this average value equation. And we end up doing the same thing that we do for a set of numbers. Just for a function, I'm adding every possible y value together when you integrate. Add all the y values together, gives you an area. But then divide by the x values, divide by 4, gives you an average y value. Does that make sense?
Somewhat.
Somewhat. Okay, so what we're going to do is we're going to set this average value equal to 15, and that will allow us to solve for c. So the average value of ft plus c from 6 to 18 would be from 6 to 18 of f of t plus c dt. And then I have to divide by b minus a in order to bring us back to calories per minute. So I don't want to change our units. So divide by 18 minus 6 should be equal to 15. Okay, and now we're going to solve for c. So first, this is 1 over 12 times the integral from 6 to 18 of f of t, which we found in the last problem, actually. We already found the area from 6 to 18 of ft, so I won't need to do that again. I'm going to break this apart. I can do that because we're adding, and integration is just repeated addition. So anytime you see an addition form when you're integrating, you can break it apart. So the integral from 6 to 18 of some constant c. And I've integrated both of these in terms of time. Okay, all of that should be equal to 15. Okay, I'm still on Kyle. When I integrate c, that's some constant, in terms of time, what will happen?
I'm sorry, could you repeat? Well, so if you integrate c,
I'm going to integrate some constant c in terms of time. So what should happen?
c squared over 2.
Close. C is a constant, not a variable. So if this was, if I derive 3x, what do I get?
If you derive 3x, you get 3x over 2 squared. 3x squared over 2.
That's if I integrate. So if I derive 3x, what will happen?
Oh, just 3.
Just 3. If I derive 9x, what will happen?
9.
Okay, so what would I have to derive in order to get c?
ct?
ct, perfect. So this is ct from 6 to 18. And then we've already said the integral from 6 to 18 of ft dt is 132 from the last problem when we got all the areas. So I'm just going to sub that in. All of that should be equal to 15. Okay, so I'm going to plug in my upper bound and subtract my lower bounds. This is 1 over 12 times 132 plus 18c minus 6c should equal 15. And we'll solve for c. So I'm going to multiply both sides by 12. 12 by 15 is the same thing as 10 by 15 is 150 plus 15 times 2 is 30. So that's 150 plus 30 is 180. Then I've got 132 plus 18c minus 6c is 12c. So I'm going to subtract 180 minus 132 to get 48. is equal to 12c, and then divide by 12 to get c is 4. What are my units? Eric.
Calories per unit square.
Close, that would be a derivative. We got an average value, so we integrated, but then we divided by the total amount of time that we covered. So if I integrate calories per minute in terms of minutes, and then I divide by minutes again, what will my units be in the end?
Can you say it again?
So what we just did was we integrated, but then after we integrated, we divided by the total amount of time. So normally, if I integrate, you'll multiply your units for y and x together. So here's f of t, and this is t. If I integrate f of t right now in terms of time, I'll have calories per minute times minutes, which would give me calories. But then we took that and divided by an amount of time. So what's my final units?
Calories per minute.
Calories
Oh,
per
minutes per cal.
calories per minute. That's a language difference. Okay. Again, if you're not sure, your average value does not change your units. Oh, it's a hard angle to write at. Units don't change. Okay, so here's our scoring guide. 1 point for our setup, which is an average value equation that we set equal to 15, and then 1 point for solving for the value of c as 4. Any questions on anything we did for A, B, C, or D? Okay, so with the tech problems, I've actually held you for almost a full hour now. So I'm going to release you. We do have homework this time that I'm going to take up. I'm going to take up the homework on Friday. You've got one more word problem to try, so that's an AP problem set kind of like this. I will answer any questions you've got on WeChat. Your partial fractions is due as soon as you can get it to me, really. I'd like to have those in the grade book, ideally by the end of the day today, but I'll keep taking it through this week. We are going to test out of integration and derivatives over the spring break, so you'll have all of spring break to finish, but I will give you the test on Thursday, the next time that I see you.
With partial fractions is the one that you assigned last week.
Yes, partial fractions is from last week. It was supposed to be due Monday. I'm going to keep taking it through this week, although if I do put it in the grade book before then, just let me know and I'll replace it when I do the next round of late grades. Okay, thank you guys very much for coming. If you still have questions, you can stick around and I'll answer anything I can. If not, you guys are free to go.
Mr. Brandon?
Thank you.
Goodbye. I heard Kyle.
A quiz or test?
Thank you.
I'm thinking I'm going to count this as a test grade, but we'll have 2 weekends and a full week to work on it through spring break. So it's kind of a good time to give a longer form test, I think.
Okay. Thank you. Bye. Have a good day.
Goodbye, you too.